Hello, I'm Graeme Norval, now an Emeritus Professor at the Department of Chemical Engineering and Applied Chemistry at the University of Toronto, and I've worked on this module with Nancy Lee, who's a PhD candidate in our department. This module is one of a series of modules on climate change, so the other modules will talk about climate modeling, modeling the consequences of climate change, and then how to design for the mitigation of those consequences. In this module, we're going to talk about energy. So hydrocarbons, be they wood or biomass, coal, oil, gas, these have been used to provide heat for millennia. But it was the conversion of heat to work, the ability to make work, whether that's electrical work or mechanical work, vehicles in motion, articles in motion, mechanical work. It was the ability to convert heat that was easy to obtain into work, which was much harder to obtain, that allowed manufacturing to be developed and to be built well away from flowing water or blowing wind. And it's that consumption of the hydrocarbons for the work conversion that's behind most of the consumption of fossil fuels. So through this course, we want to make sure that you get a deeper understanding of the differences between heat and work, to understand how thermodynamic efficiency limit the opportunities for reductions in hydrocarbon usage, and finally, to really start to think about how consumer decisions impact GHG emissions. If we go back in time, 1698, Thomas Savery patented a steam engine, the very first engine for converting heat into work to pump water from underground mines. It wasn't very good, but it led to other people to make improvements. In 1712, Thomas Newcomen built a more practical engine, the first practical working steam engine. In 1765, it was James Watt who had the idea of adding a separate condenser at the back end of the Newcomen engine, and he created the first really practical steam engine, but it was only about 2% efficient. So that means 2% of the heat released through the combustion was converted to mechanical work. In comparison, a modern nuclear power plant converts about 34% of the nuclear energy, the nuclear heat that's released, into electrical work. The rest of it is released as waste heat. And that's an important point, because we can think about this in our regular life. This is a 40-watt incandescent bulb. This is its replacement, a 5-watt LED. So replacing the incandescent with the LED, we get an 87.5% reduction in electrical consumption. In the summer, all that extra energy that's being consumed in this light bulb ends up being heat in the house, which means we add to the cooling load. But in the winter, I have to replace this heat that I'm no longer generating because I have the LED, and I have to burn more natural gas in the furnace. And that should lead us to make us realize that the transition from our energy economy is going to be hard to do. Okay, so I've indicated an article here that'll get you going, get you started on the thought, but really the key point is that it's going to be difficult. We're going to need all kinds of systems to try to make changes, not just one, but everything. And so in summary, the energy transition is going to be complicated, but the complication is due to the root issues of heat and work. And the important thing is, don't be disillusioned. Yes, it's going to be hard, and because it's going to be hard, everybody's changes are going to be small, but it's the integral of all those small changes that's going to make the difference. So I hope you learned something from this module, and have a good day.